And we'll get the slideshow set up for current slide. All right, we should be ready to go now. Any questions on anything we've done so far? Okay, good deal. Again, glad you're here. I get really bored talking to myself. So, all right, we're in Chapter 2, First Order Differential Equations, and 2.4, Exact Equations. And we did our first example of that last time. This one gets a little more involved, and they can get pretty hairy looking, but the procedure's always the same. Okay? So here's example 2, page 67. E to the 2y and minus y cosine xy. Need a few cosine log x, don't we? Or something like, no, I'm just kidding. Dx plus 2x e to the y minus x cosine xy plus 2y dy. All right, what a nice looking little problem. That must be chemical engineering, right? I'm just kidding. Okay. Yeah, I know. Yeah, yeah. You wouldn't use sine and cosines in that. Yeah. But I was just kidding. Okay. Pretty hairy looking problem. Any way you think we could do this separation of variables? No way. No way whatsoever. Okay. In fact, I can't think of any other method that we've covered so far that would even come close to this one. So, what do we try? What's our first step? Remember, just because it's written like this doesn't mean we can solve it with exact methods. So what's the first thing we've got to do? Okay. Remember, there's a test we do to see if this is indeed an exact differential. Because if it's not, hang it up. There's not much we can do with it. Remember what the test was? Okay. This part here in front of the dx is often called m of xy. Okay. Second? Yeah, okay, and that, yes, exactly. Partial with respect to what? On the left-hand side, and this is not solving the problem, this is just the test. Okay? We take the partial of that m, that first function there, with respect to what? Okay, no, the opposite of that, with respect to y. Okay? See what we get. Okay? I'm not going to write it all down. Let's just take the partial with respect to y. What do you get? 2e to the 2y. Okay, good first term. Minus cosine xy. Second. Okay. And you said a plus? Say that again now. Excellent. X, Y, sine of xy. Perfect. Okay? Now, what's the second part of the test? Partial of n with respect to x, exactly. Okay? And what does that give us? 2e to the y, good start, minus cosine xy plus xy. So you say sine of xy? Okay. Okay, excellent. Okay. And now, oh my goodness, did I copy something wrong? Yes, I did. Sorry about that. That's a 2y there. So this is a 2y here. Okay. I copied the problem wrong. Okay, what do we notice now? They are the same. Therefore, we can proceed with exact differential. In other words, this is an exact differential, so we can proceed. Now, looking ahead, and we don't use this anywhere else. Looking ahead, I think I'm going to need all the board space I've got, so I'm going to erase this. We had to do the check. We've done it, but it's not really useful anymore. We need to proceed with the problem, okay, with actually doing the solution. Okay, now, remember what the whole premise here is for exact differentials, that there has to be some function f as a function of x and y such that when you take the partials of this fy, this is going to be our solution, okay? And when you take the partial of this, and this time with respect to x, you get this thing right here. And when you take the partial of that f with respect to y, you get this thing right here, okay? And that this function is a constant, so when you take the derivative of the constant, you get 0. So that this is some constant function, okay? It's got all these things going on here, but this differential equation, its solution is for that to be a constant, okay? So, with that in mind, we know we better have it so the partial of this f with respect to x is equal to this mess. I'm sorry, to m. E to the 2y minus y cosine xy. That's what it's got to be. If that is a solution, that's got to be the partial of it. Okay? Now, what would you say the next step would be? Mathematicians usually don't like for you to do this. Actually, the way they get around it is say, multiply this by dx and that by dx. Okay? This is probably the more precise way. I've just been saying, okay? And then integrate both sides. Now, the integral of a derivative is the function, right? F of xy. Okay? Now, the key here is we're integrating this with respect to x, which means what do we treat the y's as? Constants, okay? So what's the integral of that first term? X e to the 2y. Perfect. Minus. Oh my goodness. Oh no, it's not too bad, is it? Okay. You got a cosine. Yeah, sine xy, right. Okay. And it is a minus. Okay. Sine of xy, and what did you say you also do? Exactly. You divide, because you're treating y as if it's a constant, so that would just be, you divide it here, and that wipes out that one, right? Very good. Are you through?
Plus C.
Except it's not a c anymore. It could be a function of, what are we counting as constants? Y. We're counting y as if it's a constant, so therefore our constant could be a function of y alone. Can't be any x's in it. It's got to be that. Okay? So that's what our f of xy is. Only trouble is we don't know what the g of y is. Okay? Now, if this was true, which it is, we showed this is an exact differential. So there's got to be some function f of xy so that this was the partial with respect to x, right? Well, guess what that is? The end. Yeah, that big old thing there. What is that? This is the partial with respect to x. That's
The partial with respect to y.
right. Of this function f. There's the function f. So let's take the partial. Let's take the partial of this f with respect to y. Okay? And what does that give us? Perfect. Minus cosine xy, and you put an x in front. Hey, we doubled the class size. Good. Rod's here. Okay. All right. Good to see you. Okay. We're in the middle of example 2. Just to fill you in on what we've done so far, this is on page 67, section 2.4, exact equations, and chapter 2, first order differential equations. Okay? Linear. No, just first order, not linear. Obviously not linear. Okay, and that is written as if it could be an exact equation. But we don't know that it is until we do our test. And remember what the test was? No, it's not on the board. I've already erased it. I'm just reviewing to catch you up.
I'm trying to see the test. Before we move forward, you have to see.
Partial of this.
Oh, it has to be equal to.
With respect to the other variable, y,
Has to be equal to.
has to be equal to the partial of this
With respect to x.
with respect to x. We did it and it worked. So we know there's some function, f of xy, equal to a constant, by the way, because it's, you take partials like that and give you a 0 here. This is going to be a function. Well, if that's the function that is our solution, then the partial of this with respect to x dx plus the partial of that with respect to y dy is equal to derivative of the constant, which is 0. Okay. So this has to be the partial of f with respect to x. Okay, this thing right here. So write it down. And then the trick is multiply both sides by dx. Integrate this and you get f of xy. Integrate this with respect to x, holding y as a constant, that's what we get. Now normally we have plus a constant, but because y can be a constant, we're treating it like a constant. That constant now takes the form of the g of y. Strictly a function of y, no x's in it. So what we're doing now is taking the partial of this with respect to y, would better turn out that. Okay? So that's what we're in the process of doing. And we got to the second term. And what else do we need to do? Did we finish on the second term? Yeah. Okay. And what next? No, okay. Wait, no. You're taking the derivative of this f with respect to y, partial with respect to y. You did that term, that term. What about this term? What is it? What would that be?
0.
No. You were taking with respect to y.
Yes, that'd be y.
This is g of y, just some function of y. This would be g prime.
Oh, G prime, okay.
First derivative of g. Well, maybe if I wrote it this way, it would make more sense. Let me write it in Leibniz notation. Tg dy. Okay? Because it's only a function of y, so we don't have to do partials with that. Okay? So that's our dg dy. Now we pause and take a look and see how we're doing. This is exactly that term. Yes, that's good. That's exactly that term. And this says that dg dy must be what? What's the last term?
2y.
2y, exactly. So this tells us that dg dy is equal to 2y. And guess what we can do with that? And again, pure mathematicians would say multiply both sides by dy and integrate. Okay? And when you integrate a derivative, you get the function g of y is equal to, when you integrate 2y dy, what do you get? Y squared. Okay? Now, how about the plus c here? Yeah, you can put it in there. No, well, wait. We're just taking a derivative of it. Okay. No, I'm sorry. We're going back to the beginning. And the g of y is y squared, and it could have a plus c. Okay? That could be. Okay? So now we write what our function is. F of xy is equal to x e to the 2y minus sine xy, and our g, let's leave off the plus c for now. You'll see why in a second. And your g of y is plus y squared. Because remember what this function has to be? For that to be a 0 at the end? A constant. There's where your constant is equal to c. There is your solution. A one parameter constant. You could put the constant over here and then have another constant over there and then just combine the constants. Yeah? So why not just wait and have that? Incorporate the constant of integration as well. There's your solution. A one parameter C function that is your family of solutions. All right? Now this wasn't an initial value problem, so we have no way of evaluating that. Let's see how they did. Okay. I'm trying to see why they threw a h of x in there as well. Oh, okay, I'm sorry. They're turning around and doing it the other way. Okay, I wasn't paying attention. It works both ways, by the way. You could have started with this one and said the partial of f with respect to y is this, and then done integrate y over the x is constant, come up with an h of x. That's why I said, why are they? Because they did it the other way. Doesn't matter. Well, let me take that back. Sometimes it matters. If one of these is a real bear and a half to integrate, try the other one, okay, and see if you can, my rule, be lazy. Try to find the easiest way to do the problem, okay? And go with that. They chose the other way. And what solution did they get? X e to the 2y minus sine xy plus y squared, and then they put the plus c on the same side and that it equals 0. I don't care which side you put it on. They wrote it plus c equals 0. It doesn't matter which way you do it, okay? In fact, from the very beginning, if you go back to the very front, you'll see your trying to find where they say okay, on page 65, they right after equation 2, in other words, given a one-parameter family of functions, f of x, y is equal to c, we can generate blah, 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 blah. So that's how they introduce it, so why not write it that way? But here they write the plus c equals 0. It doesn't matter where you put the plus c. Okay. Enough said? Ready for the next one? Example 3. All right. This one is an initial value problem. Okay? It doesn't even look like we should be doing here's how it gives it to you. dy dx is equal to xy squared minus cosine x sine x divided by y times 1 minus x squared, and y of 0 is equal to 2. Okay. There's our differential equation. A first order differential equation. Separation of variables, anybody? I don't think so. Okay, I think that would turn out pretty awful. Okay, your x and y are separated down there, but they're not really separated well upstairs. Okay, sure doesn't fit the linear model. I know. Doesn't look like there's much hope, does it? What can we do? Second? Yes. Let's get it into exact form. And how would that read?
Multiply the dx and multiply the 1 by
Exactly. Okay. Now, wait. Time out before we get started. I wanted to point this out to you. Because of this derivative here, I just wanted to point out a couple of things. Y cannot equal 0. Right? That derivative would be undefined. Now, maybe in the function it could be 0, but not in its derivative. What's more, what else could we say? X cannot equal 1. I agree with that. Yes, plus or minus 1. Okay? So, basically, for our derivative here, our differential equation, y can't be 0. Y can't be 0, that's horizontal axis. And x can't be minus 1 or plus 1. So we have a couple of places we need to avoid. And since we know y of 0 is equal to 2, we know we're going to be in between plus or minus 1. We cannot extend our results here or there because it can't equal plus or minus 1. Our interval has to be between plus or minus 1 because that's where our 0 is. Okay? If the initial condition had been y of 17, we'd have been out there. Or y of negative 3, we'd have been back here. It's a y of 0, so we're in between plus or minus 1. That's just not super critical here, but not a bad thing to note when you see it. Now, let's proceed. You said multiply both sides by y times 1 minus x squared, if I heard you right. Was that right? Okay. And that's going to be a dy. And over here, we're going to have xy squared minus cosine x sine x, and that's going to be times dx. Okay? Is that what you meant? Good deal. What next? Second? Okay, not yet. You don't quite have it in our form, standard form. Yes. And which you want to subtract? You want to subtract the dx side. Okay? You can. There's nothing wrong with it. I would suggest subtracting this one. And here's why. By subtracting it, I can just flip this and add it. Okay? And to me, I like the way that looks better. Okay? It's just a look thing. And it's a smaller term. And, you know, if I did the other, then you're going to need the cosine x sine x first because it's going to, yeah. So I just like it this way. So what we'll do is plus y times x squared minus 1 dy. Now this will equal 0. Do you buy that? Is that all right? You saw it was shell game. No sleight of hand here. So I'm just going to take this off to this side. Okay. Now we've got it in standard form. Okay? Now what do we do? Step 1. Okay, let's try that. Partial, we'll just call that m with respect to y. And what does that give us? Second? Okay. Yeah, okay, 2x, I got it, okay. I wasn't hearing well, okay. And that's it. Right? How about over here? What do we do? Partial of n with respect to x, okay? And what would that be?
So would you?
If it helps you.
Y2x?
Say again?
Y2x?
Yeah, y times 2x, which you could write as 2xy. Yeah, same thing. We can. It's a go. We can do it because these are indeed the same. Now, if it was helpful to you, before you did the partial, you could have multiplied through, distributed, and had x squared y minus y. If you want to do that and that helps you do the derivative faster, fine, go for it. But if you did it quite well without it, so fine. Now, this was only a test, okay, of the emergency. No, this was just a test to make sure we could do it. It's passed. We don't need it anymore. So can I go on and erase it? Because I think I'm going to need all the room I can get. Okay? But it worked. We can proceed because it is an exact differential equation. Okay. Now what does that mean? That there is some f of xy equal to some constant such that the partial of f, oh, and by the way, do you have a preference on which way we go? Let's give it a shot and see, okay? So we'll do over here, let me take it off here. We'll see, okay, that the partial of this f that we're talking about here with respect to which? Y should equal, must equal, is required to equal y times. You reckon it's going to be helpful to go and multiply through? I think so, probably. Well, all right, let's see. Okay, x squared. What you think? You do think you'd multiply? Okay, let's do it. Okay, you're the boss. I'll let you think that anyway. Okay, x squared y minus y. Okay, and then what we're going to do is multiply both sides by dy. This is how you avoid the problem of changing the partial to that. It works just as well. In fact, it's a little cleaner. Okay. Now, what does the left-hand side of that give you? F of xy. Okay. And what does the right-hand side? You're integrating with respect to y, meaning the x is treated as a constant. So what do you get? Perfect. Okay. Anything else? Yes. Plus what? Not y. X. You did this with respect to y, so you could have a function of x left over. They like h, but we'll use g because you said g. You're the boss, you think. Okay. So, what do we do with that? What do we do with that? Okay. It's okay. Say that one more time. Partial of f with respect to x, because we hope to get the thing over here, the m of xy, right? Let's see if we do. What's the partial of that with respect to x? xy squared, is that what I heard? I agree. Say again? Yeah, the y doesn't give you a thing, okay? Plus g prime of x. Perfect. Okay? Now, and I wrote it over here for a purpose, is, so we can compare it to this. So what does this tell you? That g prime had better be a negative cosine x sine x. And let me write it this way. dg dx had better be a minus cosine x sine x. Okay. And, well, hey. Foreign, right? Yeah. Make sure I put you in the right spot. Okay. We're on example 3. No. Yes, example 3, near the top of page 68. We're doing our using the exact differential procedures. It didn't look like it was that to begin with. It just gave us dy dx is equal to some really complicated looking rational expression. Okay? And it was an initial value problem, y of 0 equals to 2. Okay? And while we had it in this form, I suggested noting y can't be 0 in this derivative. Okay? And neither can x be plus or minus 1 in that derivative. Okay? Function itself might have something there, but not the derivative. Okay? So what we did next was write it into differential form. Okay? And we did this times the dy equals this times the dx. That's what we had here. Okay? Now, what we did was subtract this from both sides, and that flipped the 1 minus x squared to x squared minus 1. That let us keep the plus sign there, which I sort of like pluses better. Okay? And then we decided, because this seemed like a simpler form than that, let's go on and take the partial of that with partial of the f. Our answer is going to be f of xy equals c. Since the test worked, oh wait, I forgot. We did the test. The test is partial of this with respect to y, the opposite thing. Partial of this with respect to x, the opposite thing. Check to see if they're the same. They work. Okay? Therefore, this is an exact differential we can go to town with. Okay? So we're going to town. And we decided to start over here rather than here because this was sort of complicated looking. So we assumed that df dy, partial of f with respect to y, was this thing. Okay? So we wrote partial of f with respect to y was that thing. Then we multiply both sides by dy and integrate. This just gave us f of xy. This gave us, now remember with respect to y, your x is constant. So we did come up here and distribute this through x squared y minus y. Okay? Didn't have to, but we could. Okay? And when we do the partial, integrate this with respect to y, keeping the x as constant, that x squared just acts like a constant, and the derivative of this will be y squared over 2, so x squared y squared over 2, minus, there's no x's in this, so it's just minus y squared over 2. But your constant of integration, because you're integrating with respect to y, could have an x in it. It's not really a constant, it's a function of x. So they called it g of x. Brooks sometimes calls it h of x. I don't know. Doesn't matter. All right, so this is our f of xy. Well, this had better be the partial of this with respect to x had better turn out being that. So we take this and do the partial of this with respect to x, and sure enough, with respect to x, 2 times 1/2 is 1, x, and the y is counted as constant, xy squared. All right. Derivative partial of this with respect to x, 0. There's no x in there. It's all a constant. But the partial of this with respect to x is actually the derivative of f with respect to x, and I probably shouldn't have written it that way. I think that's what someone said, and I wrote it down. They're leading me astray. I probably should have written this as I did on the next line, dg dx. Okay? Should have written it that way. Because it's no longer, you don't need partial notation now. You just need this. Well, the partial of this with respect to x should be that. So that means that dg dx, because these two are the same already, needs to be minus cosine x dx. And that's where you walked in. So what's our next step? Integrate, yeah. And you can either multiply by dx or write it in differential form, however you want to say that. Let's just do it this way since we've been doing it that way. Integrate that, integrate that. This gives you g of x. And this gives you what? Okay. Cosine squared x over 2. That's what you said basically, right? Okay. When you say the cosine x squared, sometimes I'll write x squared, and I don't mean that. Yeah, okay, cosine squared x over 2. Is that right? Let's see. Take the derivative of this. That'd be 2 times 1/2. Yeah, that'd be cosine times derivative of cosine minus sine. Perfect. Okay. Now here, you could put the plus c here if you wanted to, but we really don't need to, because this is a boundary value problem. So let's just write it down. Well, yeah. Anywhere you want to put it, here or later, but we're going to evaluate it. So here is our function then. Oh, there it is, okay. F of xy is now x squared y squared over 2 minus y squared over 2 plus cosine squared x over 2. Okay? And let's just make that equal to some constant c. That was our original assumption. That f is some constant c. There's our parameter, one parameter system. Now I want to do something I hope you won't object to. I want to multiply everything by 2. Is that okay? Okay. May not be quite the same function, but it's going to be okay. X squared y squared minus y squared plus cosine squared x is equal to some other constant c, which is twice the previous constant. Okay? Now, we use the initial condition, which says what? What does it say? Initial condition. What is that telling us? Second? Okay, and that says anytime the x is 0, y is 2, right? So let's plug that in. Let's put a 0 for x. Boop, that's gone. Whoops, with sound effects even. Huh? Okay, and what would this be? Minus 4. And what would this be? Plus 1, you said? Is that what you said? Yeah. Second? Okay. Yeah. Okay. Is that right? My hearing's bad. So what does this tell us? -3. Okay. So we finally can write our real answer down as this: x squared y squared minus y squared plus cosine squared x is equal to -3. Or plus 3 is equal to 0. I don't care how you write that. I kind of like it plus 3 equals 0, so I have a -3 on the other side. But that's our solution. That's the solution for this differential equation with that boundary condition. Now notice we haven't violated anything, but this is only good in the interval from -1 to +1 because of that. Okay? So this isn't good out here or over there. This is good in that. Okay? And that's where we do. Yeah, they did graph it, didn't they? Yes, they did. Look at them. All right. Now, you'll see the one in the book is a little bit different. Okay? They've multiplied everything by -1, which is fine too. It's a perfectly good thing. They wrote theirs as y squared. They factored that out. But rather than x squared minus 1, they went back to 1 minus x squared and multiply that by -1 minus cosine squared x is equal to +3. Both of those are perfectly good, correct, exact answers. Okay? However, if we were doing WebAssign, they're only going to recognize one of them. I mean, and you could write it many other ways. You could write the +3 equals 0 here, or you could take this and put a -3 equals 0 there. You could put this, I mean, there's tons of ways. There's actually something else you can do. You could, instead of this, you could figure out what one, that cosine squared x is 1 minus sine squared x. You could fiddle that around, and you'll have a different looking answer, which is perfectly correct, okay? There's many different ways to write an answer, and that's one reason I don't like fighting with WebAssign. WebAssign has a lot of good tutorial help and other things like that that is well worth having, but as far as letting it tell me whether I've got right answers or not, I never trust it. Okay? And I spend more of my time working with students. Say, no, this is a correct answer. They just say, yeah, I've got to adjust that on your score. Yeah, it really gets to be a pain in the neck. well, some other part of that. Okay. Any questions? Oh, and I did want to show, since none of you have your books here, it's going to be hard to show. Here is the family of functions that satisfies. Huge family of functions. Notice y is never equal to 0, okay? It looks like it crosses there sometime, but the derivative, where it does cross there, the derivative is undefined. So that's why it's okay for y to equal 0, but the derivative is undefined there. See, every time it crosses, the derivative is undefined. Well, it doesn't look like it from some of those. No, it is. They're vertical, okay? Every time y is equal to 0. So that fits that, okay. The other thing, notice that x is never minus 1 or plus 1. And our solution puts us on this one up here. Can't be out here or there or anywhere else. It has to be somewhere between plus and minus 1, and it happens to be the curve up there. Okay? So that satisfies what we noted. I don't think the book did much about it, but anyway. Okay. All right, any questions on that before I erase? All right, now we're going to mix up some stuff, okay? The last section we did, remember we were doing linear differential equations then, first order linear differential equations, and we had those little integrating factors, that mu of x. We multiplied everything through and made sure it made a perfect derivative, a quotient rule, a product rule type thing. Well, and let me write that down, they do it here. What that came from was y prime plus p of x y is equal to some f of x. The same nomenclature, I think. A lot of times I think of that on the right-hand side as a g of x, but they do an f of x here. Okay? Now, something I say this to remind myself, or I remind all of us. In an earlier life, when you saw a p of x, you probably thought polynomial. Don't think that anymore. That p of x is any function of x alone. Can't have any y's in it, but it's definitely not restricted to polynomial functions. Any function of x, okay? We just happen to choose it here. Well, remember what we did with this? If we can write it in that form, we can proceed with, what was our first step? Integrate p of x dx. And then once you got that integrated, e to the e integral of e to x dx. That then became your integrating factor. So yeah, and you multiply that by everything and went from there. Okay, so that's it. That can be transformed into a derivative when we multiply the equation by an integrating factor. The same basic idea sometimes works for non-exact differential equation. What if we had one that was m of xy dx plus n of xy dy equals 0. That looks nice and pretty, doesn't it? Looks like it's set up to do exact. But what do we do first? Test it. Huh? Okay. Yes, take the partials with respect to the other things. Because if those partials aren't the same, this is not an exact differential equation. It isn't. It looks like one, but it's not. So what if that happens? That when you take the partial of m with respect to y, the partial of n with respect to x, they don't come out being the same. Okay? You say, throw up your hands, I quit, right? No, we don't do that. Okay. We continue. Okay? Now, that is sometimes possible to find an integrating factor, and they love the name for this integrating factor to be mu of xy. Okay? Now, remember, this doesn't have to be the same mu as before. This isn't the integral, e to the integral of blah, blah, blah. Yeah, it's not. Okay? We're just looking for one. so that when we multiply it by both sides, we get mu of xy, m of xy, dx plus mu of xy, n of xy, dy equals 0. Okay? And then we proceed, and if we can find the integrating factor that will make that pass our test, then we use it. Okay? So that's the deal that we're trying to do now, is find a mu that when you do that, you get an exact differential. Okay? So what we're heading for is that mu, I'm going to leave off the xy's now, but they're in there. Mu times m. The partial of this with respect to y needs to equal mu n, the partial of that with respect to x. Right? Okay. Now, remember these are two separate functions, different functions. So what we do here is a product rule with partials. How would that read? How would that read? Mu, second. Oh, you're doing mu sub y? Okay. Times m. Okay. Okay, the sub means you're taking the partial with respect to that. I'm leaving off the xy's now. Just, you understand? Okay. What we're doing, okay. Okay, yeah. Except because these are partials, we don't do primes anymore. We do subscripts. I'm trying to get it right. Okay, say what you just said again. Y m. How about on this side? Yeah, n. Those are n's, not m's. My hearing and my writing is not good, or not good. Okay, that's true. Okay. Now, that has to be true. All right. Now, wouldn't it be nice if we could figure out what the mu is? I mean, that's the whole problem here. If we can find the mu, we can do it, right? So let's get the mu's together and everything else on the other side. So what would that yield? Well, this doesn't have a mu in it, so let's subtract this from both sides. But this does have a mu in it, so let's bring it to the left-hand side. Okay, is that legal? Those go, those go. What do we have left? Mu times m sub y minus n sub x is equal to mu sub x n minus mu sub y m. Right? Okay. Now, here we're going to cheat. Okay? Not really. It's legal, but it seems sketchy. Okay? The whole problem here is, okay, we've already calculated these when we did our first test, right? So we have this in our pockets, right? We have these already. We know what these are. We're looking for this. What we don't know, because we don't know what this is, we don't know what those are either, right? Okay. And it's sort of chasing your tail trying to find it. So what are we going to do? Here we come up with a simplifying assumption, which sometimes seems like it's not really very fair, because our original thing was mu as a function of x, y. Here's our simplifying assumption, okay? Let's say that maybe mu depends only on x and not on y at all. So in other words, we're saying, let's not make that mu a function of y, only of x. Okay? Now, if this doesn't work, guess what we're going to do? Go back and say, well, what if we made it a function of y only and left off the x? And if neither of those work, we hang it up and try numerical integration or something else. It's probably not going to work for us. So if this is indeed true, then what we've been calling mu sub x, what we have called mu sub x, will now be mu prime, right? Because it's only derivative with respect to x. And what we have been calling mu sub y, okay, because it doesn't depend on y, that's 0. Okay, that makes the left-hand side a little bit easier to stomach, because this goes to 0. Okay, so what we have now is mu is equal to mu sub x, or I'm sorry, let's call that mu prime. I just did that and then undid it. N divided by this thing we already did, m sub y minus n sub x. Now, is there any risk of that being 0? Because we can't go around dividing by 0, right? Any risk of that being 0? No, because the first thing we did, we took the partial of n with respect to y and compared it to the partial of n with respect to x, found out they weren't the same, so if they're not the same, they can't be 0, right? So yeah, we're okay doing that, okay? Now, we still got that problem, and actually I've written it differently from the way they did. Here's our problem now. I'm going to rearrange this, okay, and do it for mu prime. And we'll write that as d mu dx. So you remember what the prime is respect to. That's equal to, we're going to multiply this, the m sub y minus n sub x, and divide by the mu, okay? No, I'm sorry. Divide by the n, getting my crazy looking things, and this is times mu. Okay, so that's what we need to happen. Okay, now here's where we still have problems, Houston. This is still a function of xy, that's still a function of xy, that's still a function of xy. And yet we have this as a function of x alone, and that is a function of x alone. So how can this be a function of x alone if these are functions of x and y? Yeah. What a pain in the neck, or some other body part, okay? Now, for that to be true, okay, if we could make that coefficient term there, that coefficient term, if we could guarantee, no, wait a minute, how have they reversed the order of that? I don't, oh wait, oh, I'm sorry, yeah, okay. sorry. I was looking at the wrong part. This needs to be a function of x alone because that's a function of x alone. So in other words, our y dependency here needs to disappear. But guess what, folks? We've already done this. We've already done that. We can subtract the 2, and we can divide by n. We know what that is. We can here's another test. If this thing, when you do this magic here, if you lose dependence on x, we found our integral. We can deal with it. Okay? If not, if this thing doesn't lose its y dependence, throw up our hands and quit? No! Never! Okay? We change it. Okay? We now make mu a function of y alone and not of x. Okay? And then we go back through our mess here and solve for, and do that. And it actually comes out really, really simple if we did the other. If this is not a function of x alone, then the derivative of the next mu, okay, with respect to y, if we make that a derivative of y alone, okay, that would have to be n sub x minus m sub x. When I looked at this, m sub y, okay, over m. And that's going to be mu. Now we're assuming function of y alone. So guess what? If when we look at this, and this is not a function of x alone, then try it the other way, n of x minus m of y, and divide it by m, and see if that's a function of y alone. If either of those is, we're really close to finding our integrating factor. Okay? Now, if neither one of them are, now we throw up our hands and quit, okay? Because we can't do it anymore, okay? So, we're not done yet, okay? If this is a function of x alone, or that's a function of y alone, then here's our integrating factor. Okay, let's I need to erase some stuff. I'm trying to think of the best stuff to erase. Okay. Can I go on and erase all this here? Okay. We've used it. We got it. We got the results of it. I don't think we need the process anymore. I don't want to erase too much. Okay. All right. Now, let's do a quick review of what we've done. First thing we do when we have a function, I didn't need this anymore. I should have erased that. It looks like that we do our first test. Partial m with respect to y, partial m with respect to x. If they're the same, go on with the exact differential. Don't mess with any of this, okay? If they're not the same, then take the difference of partial m with respect to y, which you just calculated, n with respect to x, divide it by n. If that comes up a function of x alone, you're ready to run. If not, try the other way. Partial n with respect to x, you've already done, minus partial m with respect to y, which you've already done, divided by m, which you already know. If that becomes a function of y alone, you're ready to rumble. Okay? How do we rumble? Okay? If either one of those are true, here's what our integrating factors are. If this is a function of x, and if that's the case, our integrating factor mu of x alone is, now this is where it gets somewhat similar to before, e to the integral of this thing, m sub y minus n sub x over n dx. Because you know this thing here is a function of x alone, you can take the integral of that with respect to x and go for it. Raise it to e, then your integrating factor. Go back and multiply through, you're got it.
Is the bottom one d mu of dy? Is that supposed to be m? Looks like a mu.
Okay. The y part?
On the bottom.
Okay.
On the right.
Yeah, okay, I see where you're talking about. What happens down here is I get into that thing, I lose it. So let me clear out both of these ugly things and write them better. This was y, and this is an m. Is that any better? Okay. Yeah, that's it exactly. Okay. The thing is, when I get into these symbols down here, they start doing weird things in my board. Okay, so I just didn't allow her enough room. If this is not a function of x alone, but this is a function of y alone, okay, then your integrating factor is mu sub of y alone, which is e to the integral of n sub x minus m sub y over m, now, dy. Okay? And that's a function of y alone. And then we multiply both sides by that and proceed. Okay? Now, that took a lot longer to develop than it does to put in application. Because in reality, you've already done many of these steps. You just test them, okay? And see what happens, okay? And guess what? I think that may be what example 4 is going to do, okay? All right, for me to erase? Okay? Not okay? All right. All right. Here is an awfully simple looking little, well, no, it's not that simple, but it's xy dx, that part is simple looking, plus, and this is just a polynomial, 2x squared plus 3y squared minus 20 dy is equal to 0. Now that certainly looks as if, I mean, it's in differential form, right? So the question is that an exact differential? Real easy to test, isn't it? How would you do that? Partial of? Okay. M with respect to y. And what does that give you? X. Okay, over here, let's just write it this way this time. N sub y. I think that's so much easier than writing the partial. Are you okay with that? You're familiar with that notation and everything?
It's the same thing as the same thing you did the last one. Is just
yeah, your partial of n with respect to y. That's what that means. Okay, and what would that be? No. Whoa. Okay. I messed up. We're taking the partial with respect to the other thing, remember? This is with respect to y, and that's why it's x. This is with respect to x. Okay. And what would that give us?
4x.
4x.
And that on the end? Minus 2?
Minus 20.
Oh, minus 20.
I slashed my 0. Sorry about that. Okay. Now, obviously, those are not the same. Okay? Now, the question is, what do we do with it? If we were to take this minus that, okay, the partial m with respect to y minus partial n with respect to x, okay, that's your first case. Divide it by n, are we going to lose your y's? No. In fact, we mess up our y's. Okay? But if we do the second one, which is partial of n minus partial of n with respect to x minus partial of m with respect to y, that will give us 3x, right? Divide that by xy, and you wind up with a function with y alone. Yes, that's the way to go. Do you see? Okay? So we're going to do the second case. We're going to do n sub x minus m sub y over m. That second one. And that gives us what? Just said it. What does it give us? It's not that hard. Help me, help me. What is it?
What?
N sub x minus m sub y over m. 3x over xy. Guess what? The x's go out and you get 3 over y. Say that one more time.
When you integrate it all, your mu of x is y cubed.
Okay, so we're going to integrate that dy, and that gives us what? You may have said it, I couldn't hear.
It's going to be e to the 3 ln y, which is going to be y cubed.
Okay, or you could say it as log of y cubed. I sort of like that better. Why? What's the next step? E to the that would then be y cubed. There's your integrating factor, mu as a function of y alone. And what do we do with it? We multiply it by everything in the original equation. This will now be x, y to the fourth dx plus 2x squared y cubed plus 3y to the fifth minus 20y cubed dy, and multiply that by 0 and you get 0. Okay. Nothing changed over there. Okay. Now, if you have any doubt at all, go back and do again. Okay? Take the partial of this with respect to y, and what do you get?
3x.
Say again?
4x y cubed.
4x y cubed. And you do what over here?
6x squared. That's the, you get it by x.
By x. Partial with respect to x, and what do you get?
4x y cubed.
4x y cubed in both cases? Yes, we've got it. Okay? And you don't have to do that again. We just confirmed we had it. And now we proceed just as before, except I'll ask you which one you want to start with. Yeah, I think so. Okay, our assumption here is the f of xy. There is f of xy that's constant. And what we want to do, we know then if that's true, and that's the solution to this, that then the partial of that f with respect to which? X has to equal your x, y to the fourth, right? And then the technique is multiply by dx, integrate with respect to x. This gives you f of xy. And what does that give you? X squared y to the fourth over 2 plus what? G of y, is that what you said? Okay, I'll buy that. That's a g of y. You'll do what? Okay, we're going to do the partial of this f with respect to y this time. And what will that give us? Okay, a little louder. 2x squared y. This is ugly. Let me get it looking a little bit better. 2x. Goodness gracious. 2x squared y cubed plus okay, g prime of y or dg dy. Okay? Now, what had this better be equal to? That, our n. Well, that part, the first term's perfect. This indicates that dg dy must be equal to 3y to the fifth minus 20y cubed, right? For this to be true, that has to be that, right? Because these two are equal to each other. Following it? Because the partial f with respect to y is this n over here. Partial f with respect to y is that n. Okay? So what do we do here? Multiply by dy's. Integrate. Okay? This just gives us g. And what does that give us?
Y to the 6th over 2 minus 5y to the 4th.
Okay, y to the 6th over what? 2, is that what you said? Okay.
Minus 5y to the 4th.
5y to the 4th. Okay? And you can put a constant after it if you want to, or wait and do that later. That's fine. So up here, our f of xy is now equal to x squared y to the 4th over 2 plus y 6th over 2 minus 5y 4th. That's the f, and that's equal to c. Okay? Well, as you might guess, I don't particularly like the fractions in there, so I'm going to do a slightly different f of xy and make that x squared y 4th plus y 6th minus 10 y 4th, because I multiplied everything by 2, and that's equal to some constant c. So that's the function, the solution that I suggest we have. And let's see what they did. They left the 1/2 in there, which is fine. I guess it probably makes more sense to. They left it in that form. 1/2 x squared y 4th plus 1/2 y 6th minus 5y 4th is equal to c. That's perfectly fine. That family of solutions. That was not a initial value problem, so we don't have to fiddle with it. Now, there is a remark at the end. When testing an equation for exactness, make sure that the precise form, it is of the precise form m of x, y, blah, blah, blah. Sometimes the differential equation is written g of x, y dx equal h of x, y dy, In that case, first rewrite it as g of xy dx minus h, same thing we did before, then identify and go from there. So that was nothing too new. The second little remark here, in some texts on differential equations, the study of exact equations precedes that of linear differential equations. Then the method for finding integrating factors just discussed can be used to derive the integrating factor for that. So they do it in the reverse order. So blah, blah, blah. Okay. But you see, yes? We just finished page 70. Oh, not finished. I'm going to give homework assignments there. But we were in that part. As you see, the actual practice of it is far easier than the derivation of it, which is usually the case. Okay? So do your partials just like you did. If you see, hey, they're not equal, well, will subtracting one from the other and dividing by either one m of x, is that going to make it a function of one variable alone? If it is, go for it. That becomes your integrating factor. Okay? Fairly similar to what we did before, with the exception is rather than p, you do that m minus n or n minus m over the other. Okay. So homework exercises. We already had some of these, any of the odds 1 through 19, any of the odds 21 through 25. I would do 27, 29, any of the odds 31 to 35. I would do 37, 39, and the rest of those you can look at and discuss or think through or whatever you want to do with them. That will be fine. I don't think any of the others have odd answers in the back. Up to 39, I think they do. Any that don't have odd answers in the back, don't worry with them. Okay. Now, any questions on that? I know we've lost a couple people so far. My watch broke yesterday. We still got about 20 minutes. Do we need to take a break? I know he's out now. It's a good break, so that would give him a chance to come back. So let's at least get up, stretch or something. I'm going to clear the screen here. All right, do you need this any longer? Okay. And we'll pause this for just... All right, the next section, any questions on exact equations? No? Okay. The next section is 2.5, solutions by substitutions. Okay? Now, it kind of felt like we were doing a substitution before when we did an integrating factor. It's not quite the same, but it's, in some senses a little similar. We usually solve a differential equation by recognizing it as a certain kind of equation, separable, linear, exact, and so on. Then carry out a procedure consisting of equation-specific blah, blah, blahs, right? That's what we've been doing, okay? Mathematical steps, separating variables, integrating, whatever. And that yields a solution of an equation. It's not uncommon, boy, what a statement this is, but it is not uncommon to be stumped by a differential equation. How true, okay, from day one, okay, because it does not fall into one of those classes that we know how to solve. The substitution procedures that are discussed here may be helpful in this situation. It says, often the first step in differential equations consists of transforming it into another differential equation by means of substitution. It's a lot like back when you were integrating. One of the first things you did was you found out not everything was easily integrable. Well, what if we substituted and did something else and make it, and then we can make it integrable. So it's that kind of a thing here. Okay? For example, suppose we wish to transform the first order differential equation, dy dx equal f of xy. That looks familiar, doesn't it? Okay? By substitution, y is equal to some g of u y. Okay? I'm sorry, xu. They did it the other way. Okay. Okay. In other words, we're substituting y as some other function of a different variable, for instance, u. Okay. Now, where u, excuse me, here's a big part of this assumption here. U is assumed to be a function of x alone. Y is f is a function of x and y, but y is a function of g of x and u. But u itself is a function of x as well. Okay? Now, if g possesses first partial derivatives, if it doesn't, you can't do anything with it. But if it does, then the chain rule applies here. Okay? And what we're doing here is the partial derivative of y with respect to x. If y is actually a function of g and u, then this will be a partial of f, okay, with respect to okay. Oh, he's already here. Okay. Okay. I was going to put in an intermediate step, but they leave it out. Okay. So basically what they're doing here is taking the f completely out of the picture here and just doing it with respect to here. Okay. Oh, I'm sorry. I see what they're doing. I was jumping ahead. This y, okay, partial of y with respect to g times dg dx. I'm sorry. They're not doing it that way. Okay. Back off. Okay. Derivative of y with respect to x would be the partial of g with respect to x. Okay. Times, and of course this is useless, but I'm going to write it down, dx dx, okay, plus the partial of g with respect to u du dx. That one's not useless, okay? That one was part of our assumption that u is a function of x alone, okay? So, this, of course, is just 1, okay? So, we don't need that in there. That's why I said it's useless. That's just the number 1, okay? So, what we have here, another way to write it, is dy dx is equal to g sub x, that's the partial notation, plus g sub u prime, okay? Only they write it as du dx. It doesn't really matter, but just to be consistent, I'll write it as du dx, okay? All right, now, so if we replace this dy dx with that dy dx, okay, then and replace the y in the f of xy by g of x of u, g of x and u, then the original differential equation, that one at the top there, becomes, okay, instead of dy dx, we're going to put g sub x plus g sub u du dx. Okay, that's the left-hand side. Okay, and your f your f is then written as f of x, comma, g of x and u. Okay. Make sure that's the same way they're doing it. Yeah, that's exactly. Okay. Now, if you're, and this is sort of the magic here, here's something you're going to do. Let's subtract g sub x from both sides. Okay. And divide them both sides by g of g sub u, partial. Okay. Now that goes out, that goes out. Now you have du dx is equal to f of x, g of x and u, minus g sub x divided by g sub u. Okay. And you might say, why mess with that? This whole thing here, they're going to call some new function f of x and u. Okay? Because f is a function of x and u, because f is a function of x and g, g is a function of x and u. This is a partial of f of g with respect to x, so that has x's and u's in it. This is partial of g with respect to u, that has x's and u's in it. So this whole thing here is some new function, f of x, y. That has u, sorry. So you went from this differential equation, y is dy dx equal f of xu, f of xy, to a new equation with a new dependent variable u rather than y, and the u dx is now some other function, capital F of x and u. Okay? In other words, you made a substitution, let u, well, it's sort of like let u be a function of x and y, but really they did let y be a function of x and u. Okay? And that's where you're heading. Now, without doing all that, you could have said, this is a new equation like this, and this is what it would be. But they did it all. Okay. Now, and for the life of me, I don't know why, though it may become a little more obvious, they keep changing things so much. Here, the assumption was u was a function of x alone. So now they say, if we can determine a u, which is a phi as a function of x alone, well, why don't you just keep calling it u? Why change it to phi? There's nothing special about that. And that last equation, okay, then the solution of the original differential equation is y is equal to g of x and phi of x. And in my mind, why not still call it u of x? Just put it u of x. So as we already said, it's a function of x. But no, they are now calling it phi of x. Okay. They can change the variables as often as they wish. It doesn't really matter. Okay? Now, we're going to look at three different kinds of first-order differential equations that are solvable by means of substitution. Okay? Three of these. The first we call homogeneous, and we've used that term, I think, before, and we'll use it again, and it'll have a couple different meanings. Okay? So we'll define that first. The second is called Bernoulli's equation. Okay? And then the third is called reduction to a separation of variables. Okay? Which is not nearly as simple as the other two. Well, it's okay. So first off, we got to mess with homogeneous equations. Okay? So let me clear this out of the way. And you probably forget everything we just did, but it's okay. We'll retrieve what we need to. Now here is their bizarre way of saying, which is probably mathematically quite precise, but it almost tells me nothing, okay? If you have a function f of tx, ty, okay, and that's always equal to t to the alpha of f of xy, okay? If a function possesses that property for some real number alpha, then x is said to be a homogeneous function. That's the definition of a homogeneous function. Okay? Now, I'll tell you now, we're going to use the term homogeneous for something else later. This is talking about a homogeneous function. Okay. So, here's an example of one. F of xy is equal to x cubed plus y cubed. Okay? Okay. And here's the justification. That's a homogeneous function of degree 3, since if you had taken f of tx, ty, that would be tx cubed plus ty cubed, right? That's what the function's doing. Take the first thing in parentheses, cube it, adds it to the second thing in parentheses, cube. This would be t cubed x cubed plus t cubed y cubed, and that would be t cubed times, x cubed plus y cubed, which is t cubed times alpha of x. That's what alpha of x, alpha of xy. Okay? So for alpha equal 3, that's what it is. Okay? Now, do you have to do that every time? Please say no, okay? I sure hope not, because that's real pain in the neck. Whereas alpha of xy equal x cubed plus y cubed plus 1 is not a homogeneous function. This one is, that one's not. Okay? Now, let's go back to our exact differential form, okay, which is like this: m of xy dx plus n of xy dy is equal to 0. Okay? Now that, we don't know if that's an exact differential or not, but that's at least the form we usually put it in. We have to do our test first to see if it is. But let's use that form, and we're going to say that that equation, that differential equation, is homogeneous if both the coefficients m and n are homogeneous to the same degree. Okay? Now, they go through all this stuff and they let me do a timeout here. And let me just jump to example 1. Okay? Is it? Okay. Okay. This can be said fairly quickly, I think. Okay. We'll come back and do this, but here's what we got. Example 1. I'm not going to do it now, I just want to do it. X squared plus y squared dx plus x squared minus xy dy is equal to 0. Okay? Now, to me, rather than that t's and the alphas and all that kind of stuff, here's what I look at when I'm determining if it's homogeneous. What's the degree of this term? Second? 2? Is that what you said? What's the degree of that term? What's the degree of this term? What's the degree of that term? Adam. 2. If the degrees of every term in both ones are identically the same, it's homogeneous. Isn't that so much easier than saying, if f of tx times comma ty is equal to some t to the alpha of xy, they're homogeneous. Okay? Yeah, that's true. But the other way of saying is, look at the degree of every term. You see this one right here? Degree of this term? Degree of that term? Homogeneous. Degree of this term? Degree of that term? Degree of that term? 0. Not homogeneous. Okay? That's the key. I've been trying to figure out why they wouldn't say that. Okay? But that's what makes a homogeneous function a homogeneous function. Okay? Now, we'll come back. That's why I wanted to pause there. And everything else they do is fine, but it's, to me, is almost maddening that they confuse it so much, you know. Why not keep it simple? Stupid. Okay, KISS, you know. That's the old phrase that we used to use in the Navy. So, we will pick up next time, and I'll try to determine how much of this I want to go into great detail. I think I just want to jump to the chase here, okay? And we'll pick up there on 2.5, and so have a good weekend, right? No, we'll see you Thursday. See you Thursday. I couldn't remember which day of the week this was. It's been a long week already, and it's only 2 days old. Okay, so, all right, good deal. We'll see you Wednesday.